When atoms form the total number of bonds that they like to form, the method that we used earlier will work for finding what the dot diagram is going to look like. But when we have coordinate covalent bonds, or something is forced to form a number of bonds that's not what it wants to form, it's a little more difficult to figure out. So we're going to learn another way of drawing the dot diagrams, and this way will work for any type of molecule, whether it forms the number of bonds it likes to or not. So what we're going to do is we're going to start by counting up the total number of valence electrons I have to work with. The oxygen has 6, the carbon has 4, and the other oxygen also has 6. So we have a total of 16 electrons to work with. But instead of just rearranging them on the diagram, what we're going to do is completely move them off of the atoms and put them all in a little pile off on the side, and then place them 2 at a time until everything has those 8 electrons that it wants to form. So right now, there are no electrons on my molecule. Next, we need to figure out the connectivity of the atom. And again, the one that there's only one of, the least electronegative, usually is going to go in the middle. And in order to have a molecule, I know that every atom needs to be connected to the center atom with at least a single bond. So I'm going to take 2 of my electrons and place them between each carbon and the oxygen. But instead of leaving those as 2 dots, I'm going to replace the 2 dots with a line, which represents my single bond. And now I'm going to look at how many electrons I still have left in my pile. So we started with 16. Each line uses up 2 electrons. So I've used up a total of 4. I only have 12 electrons left. Now, again, the only electrons are the ones that are drawn in the diagram right now. So this oxygen atom only has 2 electrons on it. It wants a total of 8, so it would still need 6 more. The carbon has 4 on it, so it would still need 4 more to get up to 8. And this oxygen only has the 2, so it also would need another 6. If I add that up, that means I need 6 plus 4 plus 6, a total of 16 electrons in order to make everything happy with just lone pairs. But I only have 12 left in my pile, so I don't have enough electrons. So we're going to take one of these single bonds and turn it into a double bond. So put 2 more electrons, bonding those together. But again, instead of the 2 dots, I'm going to put a line. When I do that, I use up another 2, so I'm down to 10 electrons now. But now this oxygen has 4 electrons on it. It only needs 4 more. And the carbon now has 2, 4, 6 electrons on it. It only needs 2 more. But that bond didn't affect this oxygen, so this one still needs 6. But 4 plus 2 plus 6 is 12, and I only have 10 electrons left, so I still don't have enough. So one of those single bonds, the other one, is now going to turn into a double bond between the carbon and the oxygen, which uses up another 2 electrons, so I'm down to 8 electrons. But now my carbon has 2, 4, 6, 8 on it. The carbon is happy, and this oxygen has 4. It only needs 4 more. So now 4 plus 0 plus 4 is 8, and I do have enough in order to put in lone pairs. So now I'm going to take my remaining electrons and put them in as lone pairs on the oxygens. And when I do that, that uses up my entire pile of electrons, so I've used exactly the same number that I had to work with, but everything has a total of 8 now. So when you have things that form what they like to form, that's not necessarily easier than the other way we learned. However, if we have a coordinate covalent bond or something that forms a different number than it wants to, that other way can be extremely difficult. So let's take a look now at a polyatomic ion NO3 minus. The first thing we're going to do is count up how many valence electrons we have. The nitrogen has 5. Each of my three oxygens has 6. So that gives me 23, but I have a -1 charge. That means it's gained an electron, so I actually have 24 electrons that I can work with. Next, for my connectivity of atoms, the least electronegative, the one that there's only one of, is going to go in the middle. So nitrogen is going to go in the middle, and I'm going to draw my oxygens around it. And then each atom is going to get connected to the center with a single bond. That uses up 6 of my electrons. 24 minus 6, now I have 18 electrons left. Each oxygen right now is only drawn with 2 electrons on it. So each oxygen still needs 6. The nitrogen has 6 electrons on it. It still needs another 2. So 6 plus 6 plus 6 plus 2 is 20. I don't have enough. I only have 18. So I'm going to take one of those single bonds and turn it into a double bond. It doesn't matter which one. But at this point, now the nitrogen has those 8 electrons on it. The nitrogen is happy. The oxygen has 4 on it, so this oxygen only needs 4. And I used up another 2, so I now have 16 electrons to work with. And 6 plus 6 plus 4 gives me 16. So I now have enough electrons that I can just put in lone pairs on each of the oxygens. Now, because it's a polyatomic ion, I'm going to take it and put it in square brackets with a -1 sign after it to say that this entire thing has a -1 charge.